You're changing velocity means you're accelerating. Acceleration means there is a net force. So for example, here's one situation where it may not be absolutely obvious at first what's going on. So, for example, let's say you're in a car and you're headed northbound, and so you got the road, there's your car, and you are going in that direction. And you're going to change directions. You're going to make a right-hand turn. And so the roadway, of course, is going to curve, right? And to accommodate your desire to go a different direction. And so you make this nice right-hand turn, and you're going straight to the east, continuing on your merry way. Little dashed line down the middle of the road, keep cars on the proper side of the street, no head-on collisions, all those kinds of things. So, okay, that's all well and good. Now, what does this mean, though? When you look at this, the car is traveling through a portion of a circle. So there must be a radius to this portion of the circle. The radius would be in the very center. I'm just going to eyeball it right there. And I can mark that if I want. So there, and basically I have a quarter of a circle, but there's a radius right there. Now here's the trick. So if I wanted to identify it, I could say, well, you know what? Are you sure it's a circle? Well, apart from holding the roll of tape here during the video, you just imagine the rest of this being there. Here's the rest of the circle, and essentially the roadway has its own curve in it, right? Draw that in. Just kind of swing that around. Oh, just a little bit, but you get the idea. And you got the dotted line of paint in the center. There you go. So you can see, you really can see the circle now. Even though the path itself is not a complete circle, part of it is circular here. That's very important to just, you got to be okay with that. You have to accept that. But here's the issue, right? During the turn, it's when the car, say, begins the turn, there is all of a sudden a net force pulling toward the center of the circle. What creates that force? What is causing the car to turn? No, you cannot say the steering wheel. No. There has to be something external to the car that is a force affecting it, that is an unbalanced force. So what would that be? Well, it turns out in this case, friction, our good friend. So there's no tether, there's no rope or cable or anything tying the car to a pole here in the center. And without all of that, the car still manages to change its direction. So this force that's doing that change in direction, in this case, comes from friction. Now, if you really understood friction, you would realize that this is static friction force, hopefully, as the car rolls around. Hopefully the tires are not skidding across the pavement. We have static friction, even though the car is moving. So pay attention. Sometimes the source of this centripetal force or this net force is not an obvious source. But now, bringing it all together, what we know is that there's a net force. Net forces will cause an acceleration. We also know, and this is just general, this is Newton's second law of motion right here in a nutshell, but we also know that a centripetal acceleration is related to the speed squared divided by the radius of the circle. And so we can put those together, so we can say, therefore, for what's called uniform, and what that means is constant speed, uniform circular motion, then the net force will be equal to the mass times the centripetal acceleration. But the centripetal acceleration is equal to this business here, so I can simply make that substitution. So the net force acting on the object moving in a circle is equal to the mass times the speed squared divided by the radius. And so this is a very important relationship that you want to know, and you want to be able to work with it. So, you know what, I should remain consistent for you guys. This was page 4 of these notes in the video. Now, this is all well and good. This is a very simple equation that you can work with, and the idea of swinging something around in a circle is an easy one to imagine and deal with, right? But there's something else to consider. I've been saying words like centripetal acceleration, centripetal force. And those are words you may not have heard before. And I understand that. There's another word that I'm sure you have heard before. And we have to spend a moment talking about that. And the other word you have heard I get this question a lot, and it's a good question. We hear as kids, we hear it in cartoons, we hear it in movies. People talk about this. There is a device called a centrifuge. Well, this is centrifugal force, and this is something that people have heard of. The problem with centrifugal force is it does not exist. It is a phantom. It is totally incorrect and absolutely not there. So here's what we're getting at. First, we got to talk about our own experiences, right? And the simplest thing I can point to is to say, look, and you would agree with this, when we're twirling something around in a circle, what do you feel in your hand? You feel a force pulling out. That's what you notice, right? Okay, and I would agree. I would notice the same thing. That's not a problem. There's something else. If you drive around a turn in the roadway, and let's say you drive around a little too fast through the turn, well, doesn't it feel like your body inside is being thrown this way? Don't you feel like you're getting pulled to the outside of the turn? So the car might be here at some point, and you're going pretty fast through the turn, maybe a little faster than you should be. Hopefully you're still safe, but you feel like you're kind of thrown out and pushed against that door of the car. That's what you feel. When you're on a swing set, let's see if you can imagine this. Right? And you're swinging. So imagine the seat of the swing here. And you're coming down near the bottom of that arc. What is it you feel? You feel pulled down even more than your own normal weight. It sure seems, based on our experiences, that there is this outward pulling force, right? In all these situations. The problem is it isn't there. It simply does not exist. Here's the thing. Here's what's really going on. You ready for this? Talk about myth busting. If you're going around a turn, you're going to start going straight, and the road curves, and you're just going to make this right-hand turn. You start going up this direction. As soon as the road starts to turn, you have to think about this. Your body inside the car was already on this path going straight. Newton's first law of motion, the law of inertia, essentially says, you know what, look, if your body was not disturbed by any forces, it would continue to go straight. That's what it would happen. But the car wants to go away from you. The car actually wants to go this way, and it's forced to that car has a force exerted on it, friction with the road, and it is toward the center of the circle. So that force absolutely exists. But that force aimed at the center really is a force acting on the car. And as the car's door moves to the right, it sort of bumps into you. And you think you're being thrown out against the door of the car, but you're really not. Your body's just trying to keep going straight. That's all that's happening. And yet you sense like you're being thrown outward, only because really what's happening, the door of the car is being thrown into you by this force. It's being pulled into you by that force until the turn stops, and over here now you're going straight, and that force has gone away, and you no longer feel the car door bumping into you. That's where this comes from. There is no outward force. This blue arrow is a myth and does not exist at all. There is no such thing as centrifugal force, so please keep that in mind. No, 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 no. There is only this force toward the center. Here's another way of looking at this, right? Remember this. But I feel it, you feel it too, Mr. Woods. This force pulling out on your hand. Well, yes, I do. And the trick is this. The trick here is to recognize that your hand is not the thing moving in a circle. The thing moving in a circle is this out here. And we're concerned with the forces acting on that thing. And the only force that we're concerned with that is not canceled out really is that force toward the center of the circle here. It would be equal to the force pulling out on your hand, but your hand is not moving in a circular pathway. And so, yes, this force exists, but only as a reaction. Remember Newton's third law, action-reaction. So you pull the ball in, the ball pulls your hand out. That does not mean this is centrifugal force. It is not. It is simply a reaction force. That's all it is. Your hand is not going in a circle. This is. The only force of consequence here that is not balanced is the force toward the center of the circle. That guy right there. That's what matters. There is no such thing as centrifugal force. It is something that we think we feel it. It is imagined, but it is only apparently there, like your apparent weight in an elevator. When the elevator accelerates up, you feel heavier, but you didn't suddenly gain weight. In orbit, in the International Space Station, the astronauts feel weightless, but they aren't. They still have weight. It's just a matter of their feeling, their sensation. So the same thing is fooling us here. All right, enough of that, enough of that. So here's what we have looked at, right? We have seen that with circular motion, we had to look at Newton's laws and refresh our memory a little bit about acceleration and force. Object moving in a circle could be constant speed, and that's what we're going to say. The speed will be constant, but the direction clearly is changing with time. We saw that we could carefully look at what was going on there. Let me get that out of there for you. And we saw the direction of the change in velocity. It's never headed toward the circle or toward the center, but the change in velocity is pointed at the center. And we also see that because of that, acceleration is always pointed at the center, net force is always pointed at the center. That acceleration has a name, and that is called centripetal acceleration. And here's the symbol typically used for it. It's equivalent to the speed squared divided by radius of the circle. And we also have a name for the force. That net force we can call it centripetal force. We're fine calling it net force if you want. In this case, or problems like it, it's easy to see that tension is what creates that force. Some cases, it's not so easy to see what causes it, but here friction with the road is what's causing it. And we can put the two equations together and we get this relationship, and that's going to be a good one to work with. And then finally, we figured out that this whole idea of a centrifugal force is a myth. We think it's there, we think we feel it, but no, not there at all. Hopefully this worked out for you. Let me know if you have questions. Thank you for watching. I'll catch you next time.